to a 0, and then the same thing for the next one.
Yeah, that's almost right. So Stephen, what we're defining this variable.
Right. No, I get what the.
So that's right. So we use the replace command because we've already defined the variable. But
Okay.
there's something that's also true about this. What we can do is go replace teenage mom.
Year 2002.
So what I'm saying here is, there's quadrants 3 and 4 share one thing in common. They all come from the year 1968, meaning the year 2002 data set is equal to, the marker there is equal to 0. No, it's not from the 2002 data set. So we can replace all the currently missing sectors with a 0 if we say that the year 2002 variable is not equal to yes, or it's equal to no.
I mean, wouldn't it be a little confusing actually if we went, and did it the way that Laura was saying? Because wouldn't it look like, well, wouldn't it count all the 1968? We just don't want it to count the 1968s at all, because what we're trying to do in this data set is figure out whether it's a 1 or a 0 in 2002. But it would look
so you might want it missing.
Yeah, it would look like huge, like, because it would essentially count all 1968s as zeros.
I see.
So it would give you like a crazy like result or something like that. You want it basically just to ignore it.
That's
So you might
right.
want it missing.
I think so.
There are two ways to deal with this.
Yeah.
Right. You either pick up front to change it and leave it missing, as I've chosen to, which solves Stephen's problem of if you just type in summarize teenage mom 02, you get what you were looking for, what the mean and standard deviations are, because Stephen just forgets about the missing. However, you could be very complete as Lori did and think about all 4 quadrants and all 4 possibilities and say, whenever you're going to run this variable, if you want it to be for 02, always say if year 2002 equals 1.
Right.
To restrict it that way. So there are 2 ways of dealing with this. These are all choices you have to make. Is there an easy? The easiest answer is whatever you'll remember and always do, and that's what it is. If you're going to think completely this way, be very systematic about what it is you write, that makes sense. But the point here, and the reason we went over this data, this do file, is to make clear that you have so many different options when defining data sets, and oftentimes as you get very good with STATA, you'll notice that there's one characteristic that carries over through 2 things, and you can deal with them in simple ways by just typing if year 2002 equals 0. So, good question. That was a good example. And all I'm doing here is just at the bottom of the data set, I'll just tell you, is giving, creating histograms with bin width 1 that show the age of the mom if the year is 2002 and if not. And then I just combine the graphs on the bottom. As is in the back of the last handout, I don't think I got exactly to the graph combine command in the last session, but this is a very simple, hopefully very familiar example from last time's workshop, from your problem set and everything else. So, sort of a recap of everything we've done. Any questions about this sort of this thing before I move on to random number generation, which is my favorite part of STATA? So the last thing to learn in sort of the realm of advanced data language is about random number generation. And what I want to point out to you is that, we're on page 3 of the handout now, is that there are 3 characteristics to STATA's random number generator, which is built in. It's easy to use because it's built in, and I'm assured STATA has a much better random number generator, mathematically speaking, than Microsoft Excel and than a lot of programs on the market. And as a result of more than 50 years of intense mathematical theorizing and calculation, they found out a way to get a random number generator that approximates true randomness. It isn't a truly random process. Nothing dealing with computers is a truly random process, but they've made it in such a way that it approximates true randomness. And if you'll indulge me on this point for a few minutes, the way STATA generates a random number, and this will become important later for writing simulations and other things, is to start from what's called the seed number that every STATA program has, to use what is essentially long division remainders. and then to generate random numbers. That's really all STATA does when you type in the proper commands to get it. Takes a seed, does a bunch of long division, and uses the remainders as is necessary, then create random numbers.
What's a seed?
Sure. So I'll talk about what seed is in a sec. And then it just loops back and does the process again and again as many times as you want. So, Lori asked what a seed is. That brings me to my next point. The seed is the number STATA starts with to generate random numbers. What you'll need to know are a few things. The first thing to know about the seed number is that it is exactly the same in everybody's STATA programs as a basic premise. It always starts with exactly the same seed number. And when you restart STATA, it'll start with the same seed number every time. So what you'll notice is if you're working in a computer lab with a bunch of people and you run calculations based on random numbers, you think they'd be random, but a lot of people will get pretty much the exact same answer because of the fact that the seed always starts off as the same number. That's something to remember when, for instance, you're running a simulation on a particular model and you want to more closely approximate randomness. You're going to need to do what's called resetting the seed to another kind of random number, and to sort of keep track of that if you're going to do it tens of thousands of times, which is not unheard of, or more, and write that into your do file. So let's talk now about how that works. So that's the theoretical process by which STATA generates random numbers. And here's the process, and here's what we can see in STATA. If you want to pop up STATA, that's fine, although this is not too interactive a portion of this workshop. So STATA is a great tool for testing statistical principles and also for just seeing how different commands work. So the first thing we're going to do is to look at what the result of using a random number generator would be. You should understand that in STATA you can always create your own sort of fictionalized data set by using the set observations command, set obs 10,000, let's just say. Now STATA generated 10,000 empty observations. And to fill those observations, we're going to use the random number generator command. We're going to generate a variable called random with a uniform distribution, random uniform distribution, R uniform. The parentheses are empty, will always remain empty. You have no choice to fill them with anything. There are other ways of generating random numbers for which the parentheses are not empty, but that's not the case here. If you're using STATA 9, the command is uniform, parentheses, so you just don't put on the R. Thank you. You're welcome. So hit that. And what STATA has done now is generated 10,000 random numbers from the seed using some sort of secret long division, non-linear random number generator process, which is very good, and created these 10,000 numbers. So the default, as you can see with this, is that it generates random numbers between 0 and 1, and as many as you put. So in our case, it generated 10,000 random numbers between 0 and 1. And there are special properties about how this random number generator works, which is essential to understanding what it's about. Let me just illustrate that using the summarize command. So from the summarize command, we can pick up a few things. 1, 10,000 observations, check. 2, surprisingly or not, the mean is 0.5, meaning it seems pretty evenly distributed above and below 0.5. It seems like a pretty evenly distributed data set. The standard deviation says that's also true. The minimum, very close to 0. The maximum, very close to 1.0. And what's important to understand about a random number generator command in STATA is that, well, it generates things randomly. It creates what's called a uniform density function, meaning that the chances of any number being chosen between a particular interval is exactly equal to the probability of those numbers getting chosen in the next interval. So it's uniform because as you see across the board from 0 to 1, it's pretty but not exactly even. Because STATA has generated random numbers with an equal chance of getting chosen within each bin in this histogram. Any questions about the uniform density function or anything else? And I'll show you in a second how that applies practically to doing random selection. But this is the math behind it.